Good afternoon, and thank you for joining us on our call today. My name is Christina Spearman from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Field Pressure Calibration Tips. This topic is being presented by John Lopez from Fluke Calibration. John is responsible for Fluke Calibration pressure and gas flow sales for the Eastern United States. John started his career as an avionics technician in the U.S. Army. After leaving the service, he spent several years as an electronics technician, followed by over 10 years as an applications engineer at a digital avionics company. He has been with Fluke for 4 years in technical support and sales roles. We expect today's presentation to last roughly 40 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to John.
Thank you. Hey, good afternoon, everybody. So let's go ahead and get started on this. Kind of want to start with a little bit of an overview, and then we'll delve into some topics, and we'll see how this is organized as we progress. So what are we talking about here anyway when we're saying field calibration? In general, I would define this as calibrations that are outside of carefully controlled environments. So this could include on-sites, but most especially this is in situ type locations. So down in this case here, the picture down in the basement at the main Fluke facility in Everett, Washington, or factory floors, remote stations, etc. So as we start talking about this, I'd like to kind of break this down into a couple of logical areas and show how these relate to field pressure calibration, specifically because different considerations apply with different sorts of standards and different pressure ranges, as we'll see as we go on into this presentation. So I would start by thinking about this in sort of four buckets that I put things into here, quote unquote high pressure, low pressure, draft pressure, and hard vacuum. And all of these are in quotation marks because these are not solid definitions, but rather these are categories, and of course they bleed across each other at the boundaries. For high pressure, depending on circumstances, this is something anywhere greater than 300 to greater than 3,000 psi. This is a boundary at which point folks will often be switching over to hydraulic media, not always, but often, because gas compressibility, a gas is compressible, so higher pressure generation is easier with liquid, and because of this, it may be easier, safer, and or more achievable to calibrate with a fluid media in the field or on site than with a gas or air media. If you're calibrating with higher pressure in a field situation, there's some considerations here for gas. So gas bottles. Can you take gas bottles on site? Is that allowable by local safety considerations? Can you handle them successfully, right? Do you have to carry a 6-foot cylinder up a catwalk to do some calibrations? That's not very practical. Portable gas pressure generation. This is possible. Is this achievable? Can you do it, etc.? Do you have to worry about contamination from a device under test to a gas-based standard? So as you're decreasing pressure from the device under test, do you have a potential of pulling back liquid or particulate stuff out of the external system into your standard? And another consideration is thermal or so-called adiabatic effects related to temperature. So as temperatures fluctuate, pressure fluctuates as well. Considerations with liquid is primarily liquid compatibility. So do the devices that you're testing, are they compatible with any sort of a liquid? which liquids are they compatible with? If you're doing pressure calibrations of a drinking water system, let's say, you probably don't want to use a fluid that is like, say, petroleum based. Some of these can be mitigated by what I'd call a buffer arrangement. So here's a photo that I grabbed from one of our old application notes on the Fluke Calibration side that shows an external set of tubing whereby one instrument, here the back of this instrument, uses one type of fluid, and then the device under test that's off screen here uses a separate type of fluid. And in this fitting, you would push fluid out from the device under test or from the standard, either direction. This buffer tube here already being filled with the fluid that this instrument takes, and then this union, this intermixing point here, forms a fluid buffer. Because the fluids in this case would not dissolve into one another, and because there is such little volume in this system that there's no flow or intermixing, this union would form a fluid interface and allow you to have systems that have incompatible fluids in contact with one another. Also, a consideration with high pressure liquid calibrations are thermal or adiabatic effects. As you generate pressure, you generate heat, which in turn generates more pressure. And this is evidenced as system instabilities. Some standards, as we'll see here on the next slide, some standards can help compensate for this. So for instance, if the standard that you're looking at taking to a field site is a traditional deadweight tester, it's very stable because of the floating piston. As heat, whether it's from the environment or whether it's heat that's generated from generating pressure, itself generates pressure, the floating piston changes position to accommodate and maintain the current pressure. So it's very stable. It's also very accurate. Well, there's a star by that. And you see down here in the cons of this, there's a star by this. A deadweight tester's accuracy depends largely upon the gravity that it's trimmed for. So if the gravity is trimmed for a deadweight tester in one location and it's taken to another location that has a significantly different gravity value, that needs to be accounted for. Another possible downside, something to think about for a deadweight tester, is the fact that they're generally pretty heavy because of the weights. It's not the most portable instrument in the world. An alternative to the traditional deadweight tester would be what Fluke calls an electronic deadweight tester. It's basically a digital readout and a high precision pressure reference, a transducer type reference, in a package that's similar to a deadweight tester so that it has self-contained pressure generation and etc. Good things about these: it's accurate, it's lightweight, relatively lightweight, portable. There's no gravity corrections because it doesn't use a weight stack. Cons of this, it's a sealed system. There is no floating piston, and so therefore the thermal effects have to be dealt with. It's also on the more expensive side of standards. If it's something that can do double duty in a lab and in the field, maybe that's a way to help justify that. We talked earlier about the idea of generating pressure on site for pneumatic calibrations. This would be an example of something that would do that, which is a high pressure pneumatic pump along with some sort of a reference gauge or reference device. So this is lightweight, portable. There's no gas bottles, so pressure is generated on demand. This may help satisfy safety concerns. It is a sealed system, so as with the other sealed systems, thermal effects will always come into play. As you pump, you generate pressure, you generate heat. Additional pressure will be generated as a result of that and has to be dealt with. Another type of system here is a hydraulic pump and reference gauge combination. Again, this is lightweight, portable, lowest cost of entry. So these are relatively inexpensive as calibration standards go. Again, it's a sealed system. So again, thermal effects have to be thought of and dealt with. The primary way that this is dealt with, by the way, is simply dwell time, waiting for the system to stabilize. This is often seen as a leak or instability, especially with folks that are used to using a deadweight tester. The cure for that is simply time. If the system is apparently drifting, especially as a result of an upward pressure excursion, waiting for temperatures to equalize is the solution. So let's switch over to our lower pressures. What would I define here as low pressure? This is from the high pressure cutoff region, whatever that is, down to a few PSI plus vacuum. I would consider using a pneumatic media here instead of hydraulic for several reasons. One is that it's much easier to generate and control lower pressures with a pneumatic type standard as opposed to a hydraulic standard. Trying to dial in 5 psi versus 10 psi on a hydraulic standard is going to be pretty frustrating, relatively easy on a pneumatic standard. Also, no fluid head corrections or calculations are required. So with hydraulic media, the media itself has enough mass, has enough weight behind it that it can influence the pressure. So if you're calibrating a device that's up on a wall or something like that, depending on the accuracy of the instrument, you might have to take that correction into account to account for the fact that the standard is sitting lower or higher than the device under test. Pneumatic media at the types of accuracies that we're talking about here for field calibrations can be ignored. Obviously, you're compatible with pneumatic devices. So if you have a system that uses clean air, you calibrate it with clean air. It's pretty straightforward. And you can also generate vacuum pressure, of course, with the pneumatic system. In theory, you could with a hydraulic system, but the complications are such that there's no real standard out there that has hydraulic plus vacuum. Some considerations and thoughts here on lower pressure. So contamination, as we discussed before, if you're pulling air or gas away from a device, you could also be sucking out crud from it, for lack of a better word. Things that can be done to mitigate that are external traps. So we have a picture here of a little trap that would attach to a handheld process calibrator. And the way that this works is it forces the incoming air down and then up. So it's making some right angle turns and trying to use gravity to pull stuff out of the airstream. These are sensitive to orientation, so they more or less need to be vertical. It's also a relatively small internal volume. You can see there's a drain valve on this one, so you can bleed it out once it starts to get full. I get a lot of questions about filters. Hey, can I stick a filter in here and will that help? And the answer is yes, it will, but a filter is a restriction in the pneumatic circuit, and a restriction creates a pressure differential. So the calibrations in the pressure world all depend on assuming that the pressure that's being measured at the calibration standard is the same as the pressure that's measured out at the device. So if you have a restriction between those, that is not necessarily true. In fact, in like HVAC systems, differential pressure is used to sense when filters are clogged. So you can imagine that you have a filter that you're using inline for calibration. The filter becomes clogged, and now your calibrations aren't as good as they were. And so the issues with filters all revolve around filters being clogged and not knowing when it is too clogged, application dependent, too clogged to be used in the calibration system. So rule of thumb is I would steer away from filters in favor of other solutions. Another thing to think about for vacuum ranges on low pressure is that the little kind of baby pumps that are hand pumps or process calibrator pumps from Fluke or from any vendor really, they simply aren't big enough to draw a perfect hard vacuum, negative 14.7 psi or 0 psi absolute or whatever you want to call it. They have a floor of something like negative 12, negative 13 psi. In many applications, this is fine, but if you need to draw a hard vacuum, you need some other kind of solution, like an actual vacuum pump that plugs into the wall, for instance. Low pressure standards here. So the most popular common one is a process calibrator. Example here of one of the Fluke process calibrators you see in the picture. These are kind of cool from a couple of reasons. One is they're both pneumatic and electrical. So if you're doing transmitters, the current loop transmitters, for instance, you can do complete closed loop with the process calibrator. They're battery operated, so you don't have to find a socket to plug into. They're relatively rugged. In this case, it's a transit case, so you can close the lid and it's sealed. Cons on these, usually these are one range. So if you have multiple ranges of instruments, you might have to figure out how you're going to handle that. So often these can be supplemented. In the case here, there's additional modules with different ranges that can plug into this and provide an alternate sensor. Other manufacturers have similar things or other technologies. Another type of standard out there is a hand pump and some sort of reference device, usually a gauge or a digital gauge in this case. This is lowest cost of entry. So if you're not doing a bunch of this is sort of the way to go if you're on a budget. It's battery operated. Again, one range. So you're limited to just whatever range the reference device is. You could have multiple reference devices and just swap them out on the pump. That's no big deal. But again, it's something to think about and how you're going to be using the instruments. The third category here is what I would call draft pressure. So draft pressure being less than a few psi on each side of atmosphere. And this is often delineated in units of inches of water or sometimes millibar if you're dealing with metric type units. I segregate this in its own category because there are special considerations for range and stability that come into play here that don't come into play in our other sort of pressure regimes. And especially these are noticeable when you're in non-climate controlled conditions. So digging into this in a little bit more detail, kind of an example here, range of 10 inches of water column, which might be relatively high for draft pressure items, is less than half a psi. So 100 psi, 0.05% standard, something like a typical handheld process calibrator, pretty good, is like worse than 10% equivalent at this scale. So it's just upside down. I get this question a lot, as we saw on a previous slide, with like, hey, John, I'm looking at this Fluke 3130. Can I use this to do my room pressure sensors that I have in my plant? And this has a 300 psi range, so can you? Well, yes, but will it work for your application? Probably not as is. You might have to think about this a little bit. One thing that you'd want to think about with these draft pressures is how you're going to generate pressure safely. If you have a device that has a scale of less than half of a psi and you have a calibrator that has a pump that goes to 300 psi, how are you going to use that and not overpressure your device under test? Going back to our 3130, since we're picking on that as an example, 3130 has an electric pump that has a pump button. So you press the button, you get pressure. Probably even one tap of the button would get you more than half of a psi. However, it has a fine adjust knob on it here, which allows the pressure to be dialed in Same thing on these process calibrator pumps, by the way. Same sort of a knob here to fine tune the pressure. So what that allows you to do, what that does is it connects to a little piston inside the unit that moves in or out of a small volume, which allows for finer adjustments of pressure. This is the sort of thing that if you're contemplating using one of those fine adjust knobs only for draft pressure, I would highly recommend that people test this out before going out and doing it live to determine effectively how much resolution they get out of that little knob, and to determine, is this actually going to work for my application? There are some things that can be done to help that. So adding more volume to the external system can give you more control resolution, possibly at the expense of some other factors like stability. So another issue that you'll find with draft pressure is stability. Because the relatively small difference in the case of even the full scale of a device to atmosphere, environmental influences can be significant. So somebody opening a door, for instance, will create a pressure wave across the room, just like, think of throwing a rock into a pond or something. You get waves bouncing off the edge. Depending on the sensitivity of your standard and your device, you can see this happen. You have thermal effects. So if you have a draft pressure device, if you have a draft pressure standard with the common little nylon tubing, a way to demonstrate this is to take your hand, put it around the tubing, and just hold it. The radiant heat from your hand through the plastic tubing will cause the pressure in the system to rise noticeably. And likewise, taking your hand away, the pressure will fall back down. So imagine you're in field conditions where you have the air conditioning system or heaters kicking on and off. That's going to influence the quality and the stability of your calibrations. On the Fluke calibration side, we have an application note that goes into some more details on these things. Now, the application note is not really aimed at field calibrations. It's aimed at lab calibrations with higher end lab standards, but the technical details and the issues that you encounter in both categories are the same. So the same sort of things apply to field as applies to lab, and there's a lot of good stuff that's written down in this application note. I kind of harp on this because the application note is written for lab standards and has to be interpreted for the field, but there are things that can be done that are really, really simple. So we talked about thermal effects. Down in our primary pressure and gas flow lab in Phoenix, Arizona, we do very high-end calibrations, and we deal with these kind of effects. So an example of something that's really, really simple to do that they do down there in the lab is take a sheet of bubble wrap material, go to the shipping guy, steal some bubble wrap, and put it across the top of a bench top on pressure lines. And what this does is this helps deflect and insulate drafts from the air conditioning system from influencing the pressure for low pressure or other sensitive calibrations. So it's a really simple way to do it that is really easy to achieve. This is the kind of information that you won't find explicitly in this application note, but it's the kind of stuff that you can tease out of there. How can I apply these principles to what I'm doing is what I'm getting at. Draft pressure standards. Generally, nowadays, these are process calibrators and associated measurement devices. This is an example of one from Fluke, from the industrial/handheld side. One of the things that's very nice about these is they may have a built-in pump that's ranged for the application that helps prevent overpressuring. So in this case, this is a 1 psi calibrator that has a 1 psi pump built into it. So talked earlier about trying to adapt to using something with a 300 psi pump to a less than a single psi application. Maybe you might want to consider something that's already range to that application, so you don't have to be as careful. You have some built-in guards, if you will, against overpressuring. Obviously, you get better resolution, better control resolution, that is, with a pump that's ranged closer to the application as well. Okay, so the fourth category here that I have is what I'd call hard vacuum requirements. So this is something that's more than somebody saying, hey, I just need to go to negative 15 psi. This is something where somebody has a sophisticated vacuum application. So more specifically, this is something like an ion gauge, a capacitance diaphragm gauge, et cetera, et cetera. So how can you tell this if somebody's asking about this? Well, what I often look for is the units of measure that they're asking about. As most people understand, there's a huge number of units of measure in the pressure world, and these units of measure can sometimes indicate what people are looking to do. So if people start talking about torr or millitorr, those point more towards a higher vacuum device, where somebody's talking about PSI absolute or PSIA, inches of mercury, that may point towards lower accuracy requirements. So the issue with these kind of gauges in these what I'd call hard vacuum situations isn't really the accuracy of the gauge. These aren't super difficult devices. You know, a typical good device would be like 0.25%, maybe a little bit better. The issue is how far they go down the scale, what you might call turn down. And so these things can have incredible ranges over which they are percent of reading devices. These aren't percent of scale devices, they're percent of reading devices, and they're percent of reading basically forever. So, you know, as an example here, I'm just kind of making this up. These specs don't apply to any particular device, but this is a very common one. You might have something that's 0.25% at atmosphere, and it's 0.25% at 0.76 torr, you know, almost vacuum, and then 0.0076, it's still 0.25%. So the problem here is that no matter how good your standard is, unless it's a very specialized standard to calibrate this, at some point as you go down the scale, you're going to be upside down against this device, and it has a lot more room to go. So one sort of secondary thought on these is that not all users are taking advantage of these accuracies. So there are circumstances where a normal, you know, low pressure vacuum standard would be perfectly fine. Example of this, I was talking to a customer that operates, I don't know, you kind of call it maybe a boutique steel mill, if you will. And they had a few of these gauges that they're using to basically determine whether or not the lids on the crucible, the cradle, or the pot that they melt the steel in, whether that lid is open or closed, and they melt the stuff under vacuum. The only reason that they were using these gauges is that these had a 4 to 20 milliamp loop output, and so they could read it remotely. As far as operation goes, they didn't really care about exactly how good the vacuum was down at the bottom. They just wanted to make sure it was mostly vacuum. So they were using these in equivalent to, you know, a little steam gauge that measures 30 inches of mercury. Other cases, more sophisticated users, they may want calibration all the way down. As I said here, sort of previewing on this slide, you know, they may not require the accuracy, but they might. For vacuum, large diameter tubing is definitely a help in drawing a vacuum down in a reasonable amount of time. Vacuum pumps are absolutely required to get down below the level that the little baby pumps on handheld process calibrators are capable of. More sophisticated systems even have different vacuum pumps in series. So one pump picks up where the other one stalls out. And dwell time, so similar to our thermal effects of waiting until a quality vacuum is achieved. Unfortunately here for standards, there's really nothing for hard vacuum for field calibration. An option is to use, that I've talked about with several customers, unfortunately not having anything to sell them, is a higher grade vacuum gauge used as a comparison standard and then vacuum pumps and a metering valve to set points. Sort of a clunky way of doing it, but for something that you can throw in the back of a van, that's kind of it. Industry options out there, as you see here, an example of a Fluke calibration standard, very large, very expensive, completely non-portable. This is the sort of thing that you'd have in a primary lab or the manufacturer of a vacuum gauge. Some of the manufacturers of these vacuum gauges used to or still do offer their own calibration standards. These are things that are like the size of a half-height file cabinet on casters. Possibly portable, very expensive, and somewhat non-practical for field calibration, unfortunately. And that's about it. I've talked here for about a half hour, kind of wrapping up a little bit early on this. Christina, did you have any questions?
Yes, I just wanted to say thanks, John, for the great presentation. We're going to now move on to the answer session. Just as a reminder, if you want to ask a question, please send it through the question box in your webinar controls. The first question we have is regarding the calibrator that was shown in the case. Does that supply pressure, or is an external source needed?
It supplies its own pressure. So this calibrator here has a 300 psi pump in it, battery powered pump. It's also vacuum capable. Now it's hard to see in this picture, but this calibrator also has some inputs on it for connecting an external pressure source. So if you have like a compressed air supply and you don't want to run the battery down, you can run an external gas supply into this controller or this calibrator. So it's both a pump and a external supply.
All right, let's go on to the next one. What is the right fluid to use for hydraulic calibrations?
It's a good question. It's tough because the right fluid is going to be dependent on the application. As I kind of touched on earlier, you have issues with compatibility. So some people choose to sort of pick a default that works in many cases. They may pick like distilled water, for instance, for a system because it's something that's relatively benign to most environments. They may choose to mix it with something like denatured alcohol to prevent biological growth. If the standard is sitting around for a while, you don't want to open it up and have it full of algae. Another fluid that we use in the Fluke calibration side on some of our higher end standards is a synthetic fluid called Sebacate. It's really a plasticizer. It's used to soften plastics out in industry. But we chose it because it has pretty good behavior as a calibration fluid. It's very benign. It's even used as an ingredient in makeup and sunscreen and things like that. So it's basically non-toxic. It's pretty compatible with most every material. It's non-corrosive. It behaves well under various pressures. So that is an option that we kind of put forth there. But the honest answer is the best choice is really application dependent.
Okay, which calibration standards do you typically use? Is there an ANSI or NIST calibration procedure that can be used?
There is not really a standard calibration procedure for any given thing. Unfortunately, or fortunately, depending on how you want to look at it, there's not a good document that you can point to that says here is how you calibrate every pressure device out there in the world. The U.S. government, various branches, has put out some guidance in various forms over the years, but generally this goes back to the manufacturer to determine how a device is calibrated. A specific device might take a variety of points, ascending and descending. So typically in our labs at Fluke calibration side, we'd take ascending and descending points to allow us to check hysteresis in instruments. That's not always done, especially if you're dealing with lower accuracy instruments. You may not particularly care about ascending and descending points. You might take ascending points only, for instance. You might not take as many points depending on an instrument. It's very common, for instance, that 0 and scale points only are taken. So if you have a 100 psi gauge, you take a 0 point, vent it, and you take a full scale point, and you assume linearity in between those two. The answer sounds kind of bad, but unfortunately there is not a good here is how you do it answer. It's very much individual, organization, and manufacturer dependent.
All right. Are the different size pumps interchangeable on the 718 or 719? Could you replace a 300 psi pump with a 1 psi pump?
You can, but there are some other technical differences. So in one of my previous roles here at Fluke, I got into some of the internals of the process calibrators, and there are some construction differences besides just the pump. So there's a lot of the parts here are pretty common, like this manifold fitting on here. This is the same fitting on all the process calibrators. This thing's the same. However, the way that the pressure sensor connects to the fitting and the way that the pumps work together can be different. So it's not always the case that you can just like swap out one for one. The other thing is that the pressure sensors themselves are different between the different calibrators, and the pressure sensors are not just an off-the-shelf drop-in item. The pressure sensors themselves are characterized for the performance in these systems. So if you were to do, and I've seen the results of this firsthand. If you were to do something like, hey, I blew the pressure sensor, but I'm a smart guy, I can take this apart, replace the sensor, and fix it. What you end up with, instead of a linearized sensor that reads in a linear fashion over the range, you end up with this kind of parabolic curve. You end up with this very, very nonlinear output from the raw sensor that you'd get without the linearization coefficients that we apply as part of the manufacturing process. So the answer is unfortunately no. You can't really swap ranges between the process calibrators that easily. If you're looking at a multi-range type application, what I would suggest is to get the pump, in general, to get the pump with the higher range, and then get one of the modules that plugs into the process calibrator to handle the lower, more accurate range.
All right. Are there any compatibility issues if I use a Fluke pump with a different gauge or vice versa?
No. Not in general. Generally, the main thing that you'd want to be making sure of is that the threads, or my picture of a gauge and a pump is, that the threads interface correctly here, right? That you don't have the wrong size NPT, or even worse, trying to, like, say, force fit a BSP into an NPT thread or vice versa. So a thread adapter might be necessary, but that's about it. Otherwise, the pump doesn't really know or care what's attached to it, so you can pretty much use anything.
All right. Okay, that concludes our time for today. If you have any further questions or would like to find out more about Transcat's product and service offerings, please contact us at 800-828-1470 or on the web at transcat.com. Thank you for joining us today. We hope you got something out of today's presentation and that you continue to join us for future Transcat e-learning webinars. John, thanks for your time, and have a great day, everybody.
Thanks for inviting me.
All right. Thank you. Bye-bye.